Have you ever wondered why when two skaters are about to push off each other on the ice, they both slide away gracefully? And have you ever wondered why when, someone's maybe doing some target practice at the gun range, their whole body seems to shoot back every time they take a shot? The reason for this is that there's something else that's exchanged in the physical world. And that something else is called momentum. Okay? Momentum, in many ways, you can think of as a way of quantifying the strength of an object's motion. And it's also, like energy, something that actually gets traded anytime things interact with each other. And you'll also find out that it's very, very much related to Newton's third law. Okay? So that is the focus of this week, momentum. Now, as always, I would love to share a little bit of uplifting wisdom. It seems like it's very important in these times. And this is a quote by a meditation teacher named Sharon Salzberg. And she says, "You can search throughout the entire universe for someone who is more deserving of your love and affection than you are yourself. And that person is not to be found anywhere. You, yourself, as much as anybody in the entire universe, deserves your love and affection." And I don't think this one requires a lot of explanation. I think it's just a truth that we often forget. As always, I would love to share a slide for why do we care. So Newton's third law and momentum are both very much related to different ways that objects move in the world. And this includes everything from rockets, why expelling gas from the end of a rocket is able to lift a rocket, well into space to the moon and beyond, right? And it also explains how certain types of objects move in the water, for example, an octopus. So if you look at this octopus picture here for why do we care, first of all, it's a very cool picture. Second of all, I'll just read this here. An octopus uses conservation of momentum, essentially jet propulsion, to move through the water. They do this by pushing water behind them using their tentacles. And since momentum must be conserved, we're going to find out that momentum is another quantity that is conserved. Actually, it's even more sacred conservation law than energy. So since momentum must be conserved, if they push water back, they themselves must be propelled forward. So let's suppose that you have an octopus that is pushing 0.8 kilograms of water with every thrust, and the water is moving backwards at 2.1 meters per second, and he is moving forward at a speed of 0.7 meters per second. But then the octopus suddenly sees a shark and decides to skedaddle, so he pushes harder and drives a kilogram of water at a speed of 3 meters per second. What will be this new speed of the octopus? After this lesson, you will be able to solve this problem. Okay. Now, if you go to the next slide, it's the overall introduction to momentum and what momentum should actually depend on. As I said before, momentum is a way of measuring the strength of an object's motion. It is a quantity that is exchanged during collisions. So like if I'm here and something collides with me, the momentum of this object will then get transferred to this object. And the one thing we do know is that the total momentum before and after of both objects, right, must add up to the same amount. That's this principle of conservation of momentum, which we'll be discussing. So unlike energy, though, this is the biggest distinction, momentum is a vector, so its direction is important. And we will see how that plays out as well. So we're going to play the build your own equation game again. And in order to build the equation for momentum, and I'll just start by saying momentum is usually given by the symbol P. Actually not sure why that is. And I would love the hidden points of this week's extra credit. The hidden extra credit point this week for the first 3 people who give me the answer is, why is the symbol or letter for momentum P? I don't know. Probably is like some Latin word. Anyways, so in each of these pictures, which thing has a stronger motion or more momentum? So take a look at the sumo wrestlers, right? They're not moving very fast, but which one are you sure has more momentum? The bigger dude, right? Obviously. That means momentum should depend on mass, right? Okay, now look at the tortoise and the hare. Imagine they're both, barreling along at their top speed. For the tortoise, that's not going to be very much. But which one of those do you think would have a stronger momentum? Guys, obviously the hare. So that means that momentum must also depend on velocity. All right? And I think that's it. That's really all that momentum depends on, right? So if you go to the next slide that says, how did we do? P equals mv, where P is momentum. The units are just the units of these guys, kilograms, and this is meters per second squared. So the units for momentum are just kilogram meters per second. Sorry, not squared. I think I just said squared. It's just kilogram meters per second. Okay? There's no like famous unit for momentum, like momentons or something like that. It's just this boring thing. I wish we could invent something new, though. Actually, I kind of like momentons. I think I'm officially defining 1 kilogram per meter square, a momenton. Let's see if I can get it to stick. Okay, if you go to the next slide, we will actually use this equation to find out which of these two objects has more momentum. A fly buzzing around your head at 2.6 meters per second, or a 11 kilogram sloth slowly slipping down a branch. I love sloths. You guys know how much I love sloths. Okay, so let's say momentum of the fly is going to be the mass of the fly times the velocity of the fly, right? That's simply going to be 0.05. That's 0.05 grams, right? So what is that in kilograms? Well, we add 3 zeros there. 1, 2. Yes, 3 kilograms times 2.6 meters per second. Okay, and for the momentum of this fly, I get 0.0000013 kilogram meters per second, or momentons. Check me on that. I think, no. Yeah, 0.00013. That should be right. Okay. Check me if I'm wrong. I'll fix that in the notes. So this is for the fly, and then for the sloth over here, I have that the momentum of the sloth is the mass of the sloth times the velocity of the sloth. And the mass of this sloth is, as we see here, 11 kilograms, right? And the velocity of the sloth is 0.01 meters per second. Okay. And if I multiply those guys together, I should get 0.11 momentons, or kilograms meters per second. Okay, as you can see, even though this sloth is just cruising along down this branch at this tiniest little speed of 0.01 meters per second, his bonus in mass makes it so that his momentum is still much larger than the fly. Okay. All right, so this is just the plug and chug intro of momentum. If you guys will go to the next slide, we have Serena Williams hitting a tennis ball. And for a second, I just want to look at this concept of change in momentum, because we're going to be looking a lot at collisions in this chapter. So I really would like to start thinking about the concept of how much momentum changes when you have a certain collision, okay? And so, well, here we go. We have Serena Williams, who has a tennis ball. It's approaching her racket at a speed of 30 meters per second. So if I were to draw her racket, it would be something like this. Let's shake it up with some new colors. What do you say? Here's her racket, right? And so we have a tennis ball coming in at 30 meters per second. Okay? And we want to know the change in momentum if it bounces back off in this direction at 55 meters per second. Now, one of the reasons why I wanted to show you this problem is because since momentum is a vector, the direction is important, okay? And this is actually going to be a negative 55 meters per second because it's bouncing off in the opposite direction, right? So our change in momentum, right, should be equal to P1 minus P2, right, which is mv1 minus mv2, okay, which in this case is tennis ball, looks like it's about 57 grams, so that's 0.057 kilograms, right, times the velocity coming in, which is 30 meters per second, right, minus 0.057 times negative 55, right, because it's coming back, it's bouncing off in the negative direction, so that's negative 55 meters per second. This negative and this negative are going to multiply to make a positive, right? So most people would think all you got to do is just subtract this mv for this guy minus this mv, but it actually ends up, it's adding, right? The change in momentum is going to be a bigger number because it bounces back off the other way, okay? So that change in momentum I'm getting is 4.84 kilograms meters per second. Okay? Does that make sense? So her net change in momentum when she hits that ball is 4.84 kilogram meters per second. And this is where I want to end this video. And I want to let you know that the next video, we're going to begin talking about this very, very powerful concept in the world of momentum called conservation of momentum. And it's powerful just as conservation of energy is powerful. But it's even more secure. There's even more instances in life where we can say certainly that momentum is conserved than we can energy. And we'll talk more about that in the next video.